In the early hours of April 11th, 2024, a telescope in Hawaii detected a single point of light growing brighter in a galaxy nearly 24 million light-years away. The event had started less than 6 hours earlier. Within hours, astronomers on the other side of the planet were drafting an emergency request to use one of the most powerful telescopes on Earth. They had one shot to catch something that, in all of recorded astronomical history, had never been observed in real time with this level of detail: the true shape of a supernova explosion in the moments immediately after it began. Supernovae are among the most powerful events in the known universe. A single exploding star can briefly outshine an entire galaxy of hundreds of billions of stars. The energy released in those first moments exceeds what our Sun will produce over its entire 10 billion year lifetime. And yet, despite centuries of skywatching and decades of modern telescopes scanning the cosmos, we have never managed to observe one of these explosions cleanly, precisely, and in real time during its earliest and most scientifically critical phase. That changed in 2024. The event was catalogued as SN 2024 GGI, and it has already reshaped how astronomers think about the mechanics of stellar death. What made this detection so valuable was not just its timing, but what the data revealed about the geometry of the explosion. For the first time, scientists measured the actual shape of a supernova's initial blast wave, and what they found was unexpected enough to challenge both of the leading theoretical models that astrophysicists had spent decades building. To understand why the shape of an explosion matters so much, and why catching a supernova in its first few hours is so difficult to do, we need to go back to basics and understand what a supernova actually is, what causes one, and why so much of stellar physics still relies on educated guessing rather than confirmed observation. Stars are, at their core, pressure balancing machines. The moment a star forms from a collapsing cloud of gas and dust, two forces immediately begin a competition that will define the star's entire life. Gravity pulls every particle inward toward the center. At the same time, nuclear fusion in the core produces energy that pushes outward. As long as these two forces balance each other, the star sits in a stable, roughly spherical shape and burns steadily. The fuel for that fusion is hydrogen. In the core of a star like our Sun, hydrogen nuclei are fused together under extreme temperatures and pressures to form helium. This process is called the proton-proton chain, and it releases energy according to Einstein's famous mass-energy equivalence relationship. A tiny fraction of the mass of the hydrogen nuclei is converted into pure energy, and it is that energy streaming outward from the core in the form of photons and pressure that holds the star up against its own weight. But fusion requires fuel, and fuel runs out. Over millions or billions of years, the hydrogen in a star's core gradually becomes depleted. For a star with a mass roughly 8 times or more than our Sun, this is where things get interesting, and eventually catastrophic. When the hydrogen in the core is spent, the core contracts under gravity. This contraction heats the remaining material enough to begin fusing helium into carbon and oxygen. The star expands dramatically, becoming a red supergiant, a vast, luminous object that, if placed where our Sun sits, would engulf Mercury, Venus, Earth, and sometimes even Mars. Meanwhile, the burning of hydrogen continues in a shell surrounding the helium-fusing core. This layered burning process continues as the star works its way up the periodic table. Carbon fuses into neon and magnesium. Neon fuses into oxygen. Oxygen fuses into silicon and sulfur. Each successive fuel burns faster than the last, because each successive reaction requires higher temperatures and pressures, and because the energy released per reaction gets smaller as you climb the periodic table. Hydrogen burning in a massive star can last millions of years. Silicon burning near the end of the sequence lasts only days. Then comes iron. Iron sits at a very special position in nuclear physics. The nucleus of an iron 56 atom has the lowest binding energy per nucleon of any element in the periodic table. What this means in practical terms is that fusing iron into heavier elements does not release energy, it requires energy. The fusion process, which has been the star's engine for its entire life, suddenly runs into a wall it cannot cross. Iron accumulates in the core and does nothing. It does not burn. It does not release energy. It just sits there, growing heavier and more compressed, as more iron rains down from the fusion shells above. The iron core grows until it reaches a critical mass, approximately 1.4 times the mass of our Sun, a threshold known as the Chandrasekhar limit. At this point, the electron degeneracy pressure that has been holding up the iron core against gravity, a quantum mechanical effect that prevents electrons from occupying the same state, is simply not enough. The core collapses. What happens next is one of the most violent events in nature. The collapse takes less than a second. In that extraordinary fraction of time, the iron core, a sphere roughly the size of Earth, is crushed down to a ball roughly 20 kilometers across. The outer layers of the core fall inward at speeds approaching 70,000 kilometers per second, which is 23% of the speed of light. Under these conditions, electrons and protons are forced together, fusing into neutrons and releasing an enormous burst of neutrinos. The inner core becomes a neutron star, an object so dense that a teaspoon of its material would weigh roughly 1 billion metric tons. The infalling material from the outer core slams into this newly formed neutron star and cannot compress any further. The collision creates a massive rebound, a shock wave that propagates outward through the star at thousands of kilometers per second. This is called the core bounce, and in theory, it is the event that triggers the explosion. But here is where the theory runs into serious trouble. In the milliseconds after core bounce, the outward traveling shockwave very quickly loses its momentum. It has to plow through the dense, overlying iron core, and, as it does, the intense energy of the shock tears apart those iron nuclei back into lighter particles. This process, called photodisintegration, absorbs enormous amounts of energy from the shockwave. Within roughly 100 to 200 kilometers of the center, the shockwave stalls. The explosion appears to stop before it even properly begins. And yet supernovae obviously do happen. Stars do explode. The night sky is dotted with the remnants of explosions that occurred thousands of years ago, so something must revive the stalled shockwave. Something must inject enough energy back into the system to restart the explosion and blow the star apart. Figuring out exactly what that something is has been one of the great unsolved problems in astrophysics for over 50 years. Two leading mechanisms have emerged from this investigation. The first centers on neutrinos. The second involves rapidly rotating magnetic fields and powerful jets, and it is precisely the shape of SN 2024 GGI's explosion that provides the most direct observational evidence yet about which of these two theories better describes what actually happens inside a dying star. Neutrinos are ghostly particles. They have nearly no mass and almost never interact with ordinary matter. Trillions of them pass through your body every second, originating from the sun, and you will never feel a single one. Under ordinary conditions, a neutrino can pass through a light year of solid lead without interacting with anything. But the environment just above a newly formed neutron star is not ordinary conditions. The density is so extreme that even neutrinos struggle to escape immediately. They get briefly trapped in what physicists call the neutrinosphere, a dense shell of material surrounding the neutron star. As they push their way outward through this region, a small fraction of them, roughly 1%, deposit their energy into the surrounding material. This is called neutrino heating. 1% sounds trivial, but the total neutrino output from a collapsing stellar core is staggering. In the first 10 seconds after core bounce, the neutron star radiates more energy in neutrinos than the sun will emit in its entire 10 billion year life. That is roughly 3 times 10 to the 46 joules, or 30 trillion joules of energy in neutrino form alone. 1% of that number is still an enormous amount of energy being dumped into the matter above the core. If neutrino heating is intense enough and accumulates over a long enough region called the gain region, the material above the core becomes violently unstable. Hot bubbles rise, cool material sinks, and convection develops. If the convection is strong enough, it pushes the stalled shock wave back outward and the star explodes. This is the neutrino-driven explosion mechanism, and it has been the dominant theoretical framework since the 1960s. There is one critical feature of this mechanism that matters enormously for what Yang and his team observed. It produces an inherently asymmetric explosion. The convective cells that develop under neutrino heating are not uniform or organized. They form and dissipate chaotically across different regions of the star. The shock wave gets pushed harder in some directions than others. The explosion that results has no clean axis of symmetry. It is irregular, lumpy, and multidirectional. If SN 2024 GGI was driven by neutrinos, its explosion should look like a deformed, asymmetric blob. The second mechanism tells a very different story. In the jet-driven model, the key ingredient is rotation. Many massive stars rotate rapidly, and as the core collapses, it conserves angular momentum, the same principle that makes a spinning skater accelerate when they pull their arms in. The result is a rapidly spinning neutron star, possibly spinning hundreds of times per second. As material falls onto this spinning object, it forms a disk of infalling matter surrounding the neutron star, similar in principle to the accretion disk around a black hole. Magnetic fields threading through this disk get wound up and amplified by the rotation. Think of twisting a rubber band tighter and tighter. The magnetic field lines become coiled and compressed, storing enormous amounts of energy. Eventually, these amplified magnetic fields channel a fraction of the infalling material into 2 powerful jets shooting outward along the star's rotation axis, one jet above the neutron star, one below. These jets, moving at a significant fraction of the speed of light, punch through the star's outer layers with tremendous force. They deposit their energy along a well-defined axis, the spin axis of the neutron star. The explosion that results is elongated along this axis, forming a shape that physicists describe as a prolate ellipsoid, roughly like an olive or an American football. If SN 2024 GGI was driven by this kind of mechanism, its explosion should show clear, organized axial symmetry. So which was it? Symmetric or asymmetric? Football or blob? To answer this question, Yang's team used a technique called spectropolarimetry. This is a method that measures not just the intensity of light from an object, but also the polarization of that light, the direction in which the electromagnetic waves are oscillating as they travel. Light from a perfectly spherical source would arrive at a telescope completely unpolarized, because the light from different parts of the sphere would cancel each other out in every direction. But if the source is not spherical, if it is elongated or asymmetric in some way, the light from different parts of the explosion won't cancel out perfectly, and a net polarization signal will emerge. By analyzing the polarization of the light, astronomers can determine the shape and symmetry of the source, even when it is far too small and distant to image directly. Spectropolarimetry had been used before to study supernovae, but previous attempts had always come too late. By the time astronomers could organize the necessary telescope time and point the instruments at the target, the explosion had already expanded and mixed with surrounding material. The clean initial geometry had been erased. The signal they were reading was a smeared, distorted version of what had actually happened at the moment of explosion. What made SN 2024 GGI different was timing. Atlas detected it within hours of its start. And because Yang and his team acted so quickly, drafting an emergency proposal through the night, getting emergency approval from the European Southern Observatory, and pointing the Very Large Telescope in Chile toward galaxy NGC 3621 before sunrise, they managed to capture spectropolarimetric data during the critical breakout phase. The breakout phase is the window immediately after the explosion's shockwave first reaches the star's surface. At this stage, the geometry of the explosion is still pristine. The shock has not yet had time to interact with the complex, irregular layers of gas and dust surrounding the star. The fingerprint of the core collapse mechanism is still intact in the structure of the blast. That window is extraordinarily short. Within just hours of the breakout, the ejected material begins colliding with the circumstellar medium, the gas and dust that had been shed by the star during its life. These collisions distort and obscure the original geometry. The clean signal becomes noise. Yang's team caught it just in time. The data from the Very Large Telescope's FORS-2 instrument, a powerful spectrograph and polarimeter, revealed a clear, well-defined axis of symmetry in the explosion. The polarization signal was not chaotic or irregular. It was organized. The explosion of SN 2024 GGI was, in the language of physics, a prolate ellipsoid elongated along a single axis with rotational symmetry around that axis. In plain terms, it looked like a football. At first pass, this appeared to be a clear victory for the jet-driven model. The organized axial symmetry matched exactly what magnetorotational models predicted. The neutrino-driven model, with its inherent asymmetry, seemed to be ruled out. But science rarely delivers clean, unambiguous answers, and the more carefully researchers examined both the data and the underlying theoretical frameworks, the more complicated the picture became. The neutrino-driven model has a well-documented shortcoming that goes beyond just geometry. A 2015 study published by researchers associated with the Royal Astronomical Society demonstrated that three-dimensional neutrino-driven simulations consistently produce explosions with energies roughly an order of magnitude lower than what astronomers actually observe in real supernovae. That is a factor of 10. Even under the most favorable assumptions, using maximum plausible neutrino luminosities and the most efficient energy deposition rates, neutrino heating simply does not generate enough energy to match the explosions we see in the sky. This does not necessarily mean neutrinos play no role at all. In multi-messenger astronomy, the field that combines observations of light, gravitational waves, and neutrino detection, the core collapse process, has been indirectly confirmed to produce exactly the kind of neutrino burst the theory predicts. Supernova 1987A, the closest supernova observed in modern times at roughly 168,000 light-years away in the Large Magellanic Cloud, was detected not just in light, but in neutrinos. Several underground neutrino detectors around the world registered a burst of roughly 24 neutrinos over a span of about 13 seconds, arriving roughly 3 hours before the light from the explosion reached Earth. That detection confirmed the basic picture of core collapse, but it also highlighted that neutrinos alone may not be the whole story. The jet-driven model, meanwhile, has its own serious problems when subjected to rigorous three-dimensional simulation. In two-dimensional models, jets seem to work well. They form cleanly along the rotation axis, punch through the stellar envelope, and deposit energy in an organized, axially symmetric way that drives a successful explosion. But when researchers at the California Institute of Technology extended these simulations into 3 dimensions and introduced even a tiny perturbation, a 1% wobble in the rotation axis, the behavior changed dramatically. The jets became unstable. Rather than driving cleanly outward in 2 opposing directions along the rotation axis, they began to kink and twist, spiraling around the axis like water from a garden hose that has been left lying on the ground. The jets no longer punched through the star. Instead of launching a clean, focused explosion, they produced 2 misshapen lobes of tangled, highly magnetized material that pushed outward only slowly. In many three-dimensional simulations, with even modest perturbations, the explosion simply failed to occur at all. The jets dissolved into turbulence before they could deliver enough energy to blow the star apart. And yet SN 2024 GGI clearly did explode, and it did so with an organized, axially symmetric geometry, so neither model in its simplest form seems capable of explaining what was actually observed. This is where the science gets particularly interesting. A third possibility has emerged from recent theoretical work, and it may reconcile the apparent contradiction between the observed symmetry and the instability of jets in three-dimensional simulations. What if the jet instability is not a failure mode, but actually a feature? In this revised picture, the jets are intentionally unstable and rapidly jittering. Because they cannot punch cleanly through the star along a fixed axis, they are forced to deposit their energy close to the core within roughly 1,000 kilometers of the center through a series of shocks. These shocks heat the surrounding material and create hot, pressurized bubbles. The bubbles expand, merge, and push the overlying stellar material outward. The result is an explosion driven not by a clean jet boring through the star, but by the accumulated energy of multiple small shocks deposited near the core. Crucially, even though the individual jets are chaotic and unstable, the average axis around which they jitter remains well defined. The explosion that results is not perfectly symmetric along that axis, but it retains an overall organized, prolate geometry. The explosions look like footballs, not blobs, which is exactly what SN 2024 GGI showed. This model, sometimes called the jittering-jets mechanism, was proposed by researchers as a way to preserve the benefits of magnetic field-driven jets while avoiding the fatal instability problems that plagued the simplest versions of the magnetorotational model. It sits somewhere between the neutrino-driven and jet-driven extremes, and may ultimately draw elements from both. Understanding the shape of an explosion might seem like a secondary concern compared to understanding whether the explosion happens at all, but geometry is actually one of the most powerful diagnostic tools in astrophysics. The shape of the blast directly reflects the internal physics of the dying star, the distribution of energy, the role of rotation, the behavior of magnetic fields, and the symmetry or asymmetry of the mechanism that revived the stalled shockwave. Without knowing the shape, it is almost impossible to discriminate between competing models. This is why earlier supernovae have been so difficult to study definitively. Most of what we know about supernovae comes from studying remnants, the expanding clouds of gas and dust left behind after an explosion has occurred. Objects like Cassiopeia A, the remnant of a supernova explosion that occurred around 340 years ago and sits roughly 11,000 light-years from Earth, have been studied in extraordinary detail by telescopes ranging from X-ray observatories to radio arrays. What astronomers found in Cassiopeia A is instructive. The remnant shows a distinctly asymmetric distribution of radioactive elements. Titanium-44 and nickel-56 elements produced in the explosion itself, rather than in the star's earlier burning phases, are not evenly distributed through the remnant. They are clumped and asymmetric in ways that trace back to asymmetries present from the very onset of the explosion. This pattern is consistent with neutrino-driven convection, which produces exactly the kind of irregular, asymmetric distribution of energy that would create these chemical fingerprints. But Cassiopeia A and SN 2024 GGI appear to have exploded quite differently. One shows evidence of neutrino-driven asymmetry, the other shows evidence of axially organized symmetry. This raises an important question. Are these two fundamentally different types of core collapse supernova, driven by different physical mechanisms? Or is the underlying mechanism the same, with differences in the progenitor star, its mass, rotation rate, magnetic field strength, or chemical composition determining which geometry emerges? This question cannot be answered from a single observation. To understand the full landscape of supernova physics, astronomers need a large sample of early detections. They need to catch dozens, possibly hundreds, of supernovae in the breakout phase, measure their geometries, correlate those geometries with properties of the progenitor stars, and build a statistical picture of how different types of massive stars die. This is precisely why the next generation of wide-field sky surveys is so exciting to the astronomical community. ATLAS, the Asteroid Terrestrial Impact Last Alert System, is the survey that caught SN 2024 GGI. It consists of 4 telescopes positioned around the globe, 2 in Hawaii, 1 in Chile, and 1 in South Africa. Together, these 4 telescopes scan the entire visible night sky every 48 hours, imaging each region 4 times per night. This rapid cadence is designed to catch fast-moving transient events, near-Earth asteroids that might threaten our planet, but also fast astrophysical transients like supernovae, tidal disruption events, and gamma-ray burst afterglows. The combination of global coverage and frequent revisits is what made it possible to catch SN 2024 GGI so early. When the survey imaged the region of sky containing NGC 3621 on the night of April 10th, the location of the supernova appeared blank. When it imaged the same region less than 6 hours later, a bright spot had appeared that had not been there before. The automated alert system flagged the change and notified the astronomical community almost immediately. This is the power of systematic, automated sky surveys. No human astronomer sat watching a monitor waiting for a supernova. The software did the watching, and the software caught it. But ATLAS is just the beginning of what is becoming a revolution in time-domain astronomy, the study of how the universe changes over time, from timescales of milliseconds to timescales of billions of years. The Vera C. Rubin Observatory, located in northern Chile on the Cerro Pachon Ridge at an altitude of roughly 2,662 meters, began regular survey operations in 2025. It carries what is currently the largest digital camera ever built for astronomical use, a 3,200,000,000 pixel mosaic detector that covers a field of view roughly 49 times the area of the full moon in a single image. The survey it is conducting, the Legacy Survey of Space and Time, will image the entire southern sky every 3 to 4 nights, going roughly 10 times deeper than ATLAS. At this depth, Rubin will detect supernovae in galaxies far more distant than any current wide-field survey. It is expected to catalogue approximately 10 million transient events per year. To put that number in perspective, the total number of supernovae ever observed across all of astronomical history up to the present is in the tens of thousands. Rubin will find more supernovae in a single year than we have collectively discovered in the entire history of the field. But raw detection numbers are not the point. What matters is the ability to follow up detections rapidly with spectroscopic instruments that can measure the polarization, velocity, and chemical composition of the explosion in its earliest moments. The challenge ahead is not finding supernovae, it is building the infrastructure to characterize them fast enough. NASA's PHEREX mission, which launched in 2025, contributes a different but complementary capability. It is a low-resolution, spectroscopic all-sky survey operating in near-infrared and optical wavelengths. While it cannot match the depth or resolution of the Very Large Telescope's FORS-2 instrument that Yang used to study SN 2024 GGI, it provides continuous, all-sky coverage that helps bridge the gap between initial detection and detailed follow-up. PHEREX can provide rapid spectral information about newly detected transients, helping prioritize which objects warrant immediate intensive follow-up with larger telescopes. The Sloan Digital Sky Survey, one of the most productive astronomical surveys in history, released a major new dataset in 2025 as well. While the Sloan survey is primarily designed for different science goals, mapping the large-scale structure of the universe, cataloging billions of galaxies, studying the properties of stars and quasars. Its data provides crucial context for supernova science. Knowing the properties of the host galaxies in which supernovae occur, including their star formation rates, chemical abundances, and distances, helps astronomers interpret the properties of the explosions they observe. Together, these new tools represent a fundamental shift in how astronomy operates. The era of building a single, specialized telescope and pointing it at one object for months at a time is not over, but it is being supplemented by an era of industrial-scale sky surveys that automatically detect, classify, and trigger alerts for transient events faster than any human observer could manage. What this means for supernova physics specifically is that the sample of early phase detections should grow from a handful previously, just a few cases caught by chance, to dozens or hundreds per year within the next decade. Each new early detection is an opportunity to measure explosion geometry during the breakout phase. Each new measurement is a data point that can confirm, refine, or challenge the theoretical models being developed to explain what happens inside a dying star. The question of failed supernovae is particularly interesting in this context. Not every massive star that undergoes core collapse produces a visible supernova explosion. In some cases, particularly for the most massive and rapidly rotating stars, the collapsing core may form a black hole before the shock wave can be revived. The entire star simply collapses, quietly, into a black hole. No explosion, no bright light. Just a star that was there and then is not. There may be several such events happening in our galaxy every century, and we would never know about them unless we happen to be watching a specific star continuously and noticed it disappear without exploding. There is in fact one candidate for this kind of event, a red supergiant in a nearby galaxy known as N6004, which was observed in 2009 and appeared to undergo a brief brightening, possibly indicating the onset of a collapse, and then simply vanished. Follow-up observations found no bright supernova remnant. If this was indeed a failed supernova, it would be the first directly observed case of a star collapsing silently into a black hole. Understanding failed supernovae requires understanding what determines whether the shockwave revival mechanism succeeds or fails. The geometry of the explosion, the very thing that Yang's team measured for SN 2024 GGI, may be one of the key diagnostic indicators. If the explosion develops an organized, axially symmetric geometry early on, it may indicate that a magnetorotational mechanism is operating efficiently and the explosion will succeed. If the geometry is irregular and the shockwave revival relies on chaotic neutrino heating, there may be cases where the heating is insufficient and the star collapses without exploding. Catching more supernovae and more failed supernovae in their earliest moments is the only way to build the statistics needed to test these ideas. There is also a connection to gravitational wave astronomy that could prove transformative over the coming decades. Core collapse supernovae are expected to produce gravitational wave signals, ripples in space-time, caused by the asymmetric acceleration of enormous amounts of mass. The neutron star formation, the sloshing and convection of dense material, and the potential formation of jets all create asymmetric mass distributions that, when accelerating, emit gravitational waves. The challenge is that the gravitational wave signal from a core collapse supernova is expected to be substantially weaker than the signals from the compact binary mergers, neutron star collisions, and black hole mergers that the LIGO and Virgo detectors have been detecting since 2015. Detecting a gravitational wave signal from a supernova would require either an extremely close event, a supernova within our own galaxy, or a significant improvement in detector sensitivity. The next generation of gravitational wave detectors, including the proposed Einstein telescope in Europe and the Cosmic Explorer in the United States are designed to be roughly 10 times more sensitive than current instruments. At that sensitivity, they would potentially be able to detect gravitational wave signals from core collapse supernovae in nearby galaxies distances comparable to that of SN 2024 GGI at 23.8 million light-years. If a gravitational wave detection could be correlated with a simultaneous optical and neutrino detection of a supernova, the scientific return would be extraordinary. The gravitational wave signal encodes information about the motion of mass deep inside the star during the collapse and explosion information that light cannot provide, because light can only escape from the outer layers of the star. Combining gravitational wave data with the spectropolarimetric data that Yang's team measured for SN 2024 GGI would provide an unprecedented, multi-messenger picture of what happens during those critical milliseconds when the shockwave stalls and is revived. The last time a supernova was close enough to provide multi-messenger science was 1987A. That event, in the Large Magellanic Cloud, was detected in neutrinos and in light across the full spectrum from gamma rays to radio waves. It transformed our understanding of supernova physics and confirmed, for the first time directly, that the core collapse process produces the neutrino burst that theory predicted. The neutrinos from 1987A were detected roughly 3 hours before the light because the neutrinos escaped immediately after core bounce, while the light had to wait for the shockwave to reach the stellar surface. If a similar event occurred in our own galaxy today, and given the number of massive stars in the Milky Way, one is statistically expected roughly every few decades, the science would be incomparably richer than it was in 1987. We have better neutrino detectors. We have gravitational wave detectors that did not exist in 1987. We have wide-field optical surveys that would catch the brightening immediately. We have spectropolarimetric capabilities on large telescopes that could be deployed within hours. The combination of all these instruments deployed simultaneously on a single nearby event would be the most powerful multi-messenger astronomical campaign in history. But we cannot count on a nearby event. The Milky Way's last confirmed naked-eye supernova was Kepler's star in 1604, over 400 years ago. Statistically, we are overdue. But stellar death does not follow a schedule. In the meantime, the science advances event by event, detection by detection. SN 2024 GGI was caught because Atlas happened to scan the right patch of sky at the right time, and because a team of astronomers in Beijing recognized what the data meant and acted with extraordinary speed. The next early detection might come from a different survey in a different galaxy, tomorrow or in 5 years. Each one is an unrepeatable experiment, a window into physics that cannot be reproduced in any laboratory on Earth. What Yang and his colleagues demonstrated in 2024 is that the window is catchable, that if you build the right instruments, write the right software, and are willing to spend sleepless nights drafting emergency telescope proposals, you can measure the geometry of a star's death within hours of it happening for the first time. And what that geometry tells you about the mechanism of the explosion has the power to transform theories that have been debated for half a century. The prolate, football-shaped geometry of SN 2024 GGI does not definitively solve the supernova problem. Both the jet-driven and jittering-jets models can produce symmetric explosions. The role of neutrinos remains genuinely uncertain. Other supernovae show the asymmetric structures associated with neutrino-driven convection. The differences between Cassiopeia A and SN 2024 GGI suggest that not all massive stars die in the same way, that the physics of the explosion may depend sensitively on properties of the progenitor star that we do not yet fully understand. What we need now is more data, more early detections, more measurements of breakout phase geometry, more correlations between explosion shape and progenitor properties. More multi-messenger events that let us combine optical, neutrino, and gravitational wave signals into a single coherent picture of core collapse. The tools to gather that data are being deployed right now. Rubin is scanning the southern sky. Spherex is mapping the all-sky near-infrared spectrum. Atlas is sweeping the full sky every 2 days. And when the next great opportunity arises, when the next bright transient appears in the night sky within hours of explosion, there will be more telescopes ready to catch it, and more scientists ready to stay up through the night to make sure the chance is not missed. The universe has been exploding stars for nearly as long as stars have existed, roughly 10 billion years of continuous stellar death, with each explosion seeding the galaxy with the chemical elements that would eventually form planets, and, on at least one of them, living things. The carbon in our cells, the oxygen we breathe, the iron in our blood, all of it was forged in stellar cores and scattered across space by explosions like the one Atlas detected in April of 2024. We have been living with the consequences of supernovae for our entire existence. It is only very recently, really only in the last few years, that we have had the tools to watch them happen. SN 2024 GGI was the first time we measured the true shape of one of these explosions as it occurred. It will not be the last. And each new measurement brings us closer to understanding one of the fundamental questions in modern astrophysics. How does a dying star, in its final moments, manage to blow itself apart? The answer is not fully known, but for the first time, we are asking the right question while watching the explosion happen in real time. And that, in the history of our attempt to understand the cosmos, is a significant step forward. To fully appreciate what makes SN 2024 GGI so scientifically valuable, it helps to understand just how rare a clean, early supernova detection really is. The universe is full of exploding stars. In a galaxy like the Milky Way, a supernova occurs roughly every 50 to 100 years on average. Across the observable universe, which contains somewhere between 200 billion and 2 trillion galaxies, supernovae are happening constantly, roughly several per second across all of cosmic space. They are not rare events in an absolute sense, but catching them at the right moment is enormously difficult, for reasons that go beyond just the unpredictability of when a particular star will explode. The problem is that massive stars, the kind that end as core collapse supernovae, are rare in any given galaxy. Our Milky Way contains perhaps a few 100 billion stars, but the fraction of those that are massive enough to end as supernovae stars, with roughly 8 solar masses or more at birth, is tiny. Most stars are small and dim, like our Sun or smaller, and will end their lives quietly as white dwarfs rather than spectacular explosions. The massive stars burn brightly but briefly, living only millions of years before they exhaust their nuclear fuel. They are statistically uncommon. Moreover, massive stars tend to form in regions of active star formation, dense molecular clouds, where gas is collapsing into new stars. These regions are often embedded in thick clouds of dust and gas, which absorb light and make the dying star difficult to observe even when it does explode. Some supernovae are dust obscured to the point of being nearly invisible in optical wavelengths and are only detectable in infrared or radio waves. The dust that surrounds many of the most massive and youngest stars acts as a veil, hiding their deaths from optical surveys like Atlas. There is also the issue of what astronomers call the progenitor identification problem. To understand how a particular supernova happened, it helps enormously to know what the star looked like before it exploded. What was its mass? Its luminosity? Its surface temperature? Was it a single star or part of a binary system? Had it been losing mass in the years or centuries before its death? Identifying the progenitor star requires having archival images of the supernova's host galaxy taken before the explosion occurred ideally deep, high-resolution images taken with the Hubble Space Telescope or a comparable instrument. When a supernova occurs in a galaxy that has been previously imaged, researchers can look back through the archive and try to identify which star in the pre-explosion images corresponds to the location of the explosion. If they can find a match, they gain access to the progenitor's observed properties and can begin constructing a complete picture of that star's final state before death. This has been done successfully for a handful of supernovae. The progenitor of SN 2003 L2 in the galaxy M74 was identified as a red supergiant with a mass of roughly 7 to 8 solar masses, right at the lower boundary of what theory predicts for core collapse. The progenitor of SN 1987A was the blue supergiant Sangelik -69 degrees 202, a star that had been catalogued decades earlier and was observed directly during and after the explosion. But most supernovae occur in galaxies that have not been previously imaged at the necessary resolution, or in regions too crowded or too distant to isolate a single progenitor star. For the majority of supernovae, the progenitor remains unknown, which limits what can be inferred about the relationship between the star's properties and the character of its death. This is one reason why the study of supernova remnants within our own galaxy is so important. Cassiopeia A, the remnant of a supernova that exploded roughly 340 years ago, is close enough and bright enough that it has been studied by virtually every major telescope in operation. X-ray observations by the Chandra X-ray Observatory reveal a complex asymmetric structure of hot gas threading through the remnant, with filaments of material moving at thousands of kilometers per second. Infrared observations by the Spitzer Space Telescope and later the James Webb Space Telescope have mapped the distribution of dust grains in the remnant dust that was produced in the explosion itself and contributes to the interstellar medium of the galaxy. Radio observations have tracked the motion of the shock front as it expands into the surrounding interstellar gas. The James Webb Space Telescope's observations of Cassiopeia A, released in 2023, provided a particularly striking view of the remnant structure. The near-infrared and mid-infrared images revealed previously unseen fine structure in the explosion, thin threads and curtains of material that had been invisible in earlier observations. These structures trace the turbulent asymmetric mixing that occurred as the shockwave propagated through the star and then into the surrounding material. The pattern of chemical elements visible in the Webb images, oxygen, sulfur, argon, neon, matches theoretical predictions from models of silicon and oxygen burning in the star's final hours before collapse. But Cassiopeia A is a remnant, not an explosion in progress. What we see today is the result of 340 years of expansion and interaction with the interstellar medium. To truly understand the initial conditions of the explosion, the geometry at the moment of core bounce, the distribution of energy deposited by the revival mechanism, we need to catch the explosion itself. The closest thing to catching Cassiopeia A in real time would be a supernova in our own galaxy. And while galactic supernovae are rare on human timescales, they do occur. The history of astronomy includes several confirmed cases of naked-eye supernovae visible from Earth, observed before the invention of telescopes. SN 1054, observed by Chinese and possibly Arab astronomers, produced the Crab Nebula, now one of the most extensively studied objects in the sky. The Crab pulsar at its center is a neutron star rotating roughly 30 times per second, generating a pulsar wind nebula that has been observed across the full electromagnetic spectrum from radio to gamma rays. The Crab Nebula is in some sense the best studied supernova remnant in history, yet it was caught by naked-eye observation 1,000 years ago by astronomers who had no way of knowing what they were seeing. SN 1006, visible from Earth and described in records from China, Japan, Europe, and the Arab world, was so bright at its peak that it could cast shadows at night. It was visible in daylight for weeks. Its remnant, known as SNR 1006, lies roughly 7,000 light-years away in the constellation Lupus and has been mapped in X-ray, optical, and radio wavelengths. The remnant shows a roughly bilateral symmetry, two bright lobes on opposite sides of a dim center, which some researchers have interpreted as evidence of an axially organized explosion, similar to what Yang observed for SN 2024 GGI. Tycho supernova, observed in 1572 by the Danish astronomer Tycho Brahe, was a different kind of event, a type Ia supernova, the thermonuclear detonation of a white dwarf, rather than a core collapse event. It was important historically because Brahe's careful measurements demonstrated that the new star was genuinely far beyond the sphere of the moon, contradicting the Aristotelian doctrine that the heavens were immutable. The Tycho supernova remnant is still expanding today, studied by modern X-ray telescopes as a textbook example of a thermonuclear explosion's chemical fingerprints. Kepler's supernova in 1604 is the most recent confirmed naked-eye supernova in the Milky Way. It appeared in the constellation Ophiuchus and was observed by astronomers across Europe and Asia. Johannes Kepler, then serving as imperial mathematician in Prague, wrote a detailed treatise about the new star, noting its changing brightness and color over the months it remained visible. The remnant of Kepler's supernova lies roughly 20,000 light-years away, making it one of the most distant known galactic supernova remnants, and has been studied by Chandra, Hubble, and Spitzer in detail. The fact that the last naked-eye galactic supernova was over 400 years ago does not mean the Milky Way has stopped producing them. It simply means that the more recent ones have occurred behind thick dust clouds in the plane of the galaxy, invisible in optical light. Several candidate remnants from supernovae that would have been visible from Earth within the past few hundred years have been identified by radio and X-ray surveys, objects that appear to be young supernova remnants but have no corresponding historical records of a bright new star, presumably because the intervening dust absorbed the light before it reached us. The most notable of these is Cassiopeia A itself. The explosion that produced it occurred sometime around 1680, based on the expansion rate of the remnant. Yet, there is no confirmed historical record of a bright new star seen from Earth at that time. One possible explanation is that the explosion was initially obscured by dust, with only a brief and faint optical brightening escaping through the dust that might have been mistaken for a variable star. Another is that the Progenitor underwent significant mass loss before exploding, ejecting enough material to shroud the explosion. Either way, one of the most spectacular explosions in recent galactic history went essentially unobserved. This underscores a persistent limitation of optical astronomy. The universe is not transparent. Dust absorbs and scatters optical and ultraviolet light, while being largely transparent to infrared and radio waves. Wide-field surveys like ATLAS and Rubin work primarily in optical and near-infrared wavelengths. They will catch supernovae in relatively unobscured locations, but may miss a fraction of events that occur in heavily dust-enshrouded regions. Complementary infrared surveys are important for catching the full census of stellar explosions. The Spitzer Space Telescope, before it was decommissioned in 2019, conducted several all-sky infrared surveys and discovered a number of heavily dust-obscured supernovae in nearby starburst galaxies. Galaxies undergoing rapid bursts of star formation, where the dense interstellar medium absorbs much of the optical light from new explosions. Some of these events were discovered months after they began, because they simply could not be detected in optical wavelengths at all. The next generation of wide-field infrared surveys, including the Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will help close this gap. Beyond detecting and characterizing individual supernovae, there is a broader cosmological importance to understanding these events accurately. Type Ia supernovae, the thermonuclear kind, not the core collapse kind, became famous in the 1990s as cosmological distance indicators. Because type Ia supernovae are produced by a roughly standardized process, the thermonuclear detonation of a white dwarf that has accreted or merged with enough material to cross the Chandrasekhar limit their peak luminosities are roughly similar from event to event. After applying a calibration based on the shape of their light curves, by comparing how bright they appear with how bright they should be, astronomers can calculate how far away they are. This distance measurement technique was used by two independent teams in 1998 to discover that the expansion of the universe is accelerating a discovery that earned the Nobel Prize in Physics in 2011 and revealed the existence of dark energy, the mysterious force apparently driving the accelerating expansion. The entire case for dark energy rests on the assumption that type Ia supernovae are reliable standard candles. But our understanding of exactly what produces a type Ia supernova, and whether there might be subtle systematic variations in their luminosities that could bias the cosmological measurements, remains incomplete. Different progenitor scenarios, single degenerate systems, where a white dwarf accretes from a companion star, versus double degenerate systems where two white dwarfs merge, might produce subtly different explosions. If the mix of progenitor scenarios changes as you look at higher and higher redshifts, that is, earlier and earlier times in cosmic history, the calibration of type Ia supernovae as standard candles might be subtly off in ways that could affect the inferred cosmological parameters. Core collapse supernovae, while not standard candles in the same way, have their own relationship to cosmological measurements through the study of nucleosynthesis. The heavy elements produced in stellar explosions from carbon and oxygen through iron and nickel, and all the way up to the heaviest elements on the periodic table, accumulate in the interstellar medium over cosmic time. The chemical evolution of galaxies and the availability of the elements needed to form rocky planets, and ultimately life, depends on the rate and efficiency with which core collapse supernovae process and distribute these elements. Understanding the explosion mechanism, how much energy goes into the kinetic energy of the ejected material, how much goes into neutrinos, how much goes into the neutron star, directly affects the predicted yields of different elements from supernovae. The asymmetric geometry revealed by spectropolarimetry affects which parts of the star get heated and ejected, and therefore what chemical elements end up in the remnant and in the interstellar medium. Getting the geometry right is not just a matter of academic interest, it affects the predicted chemical abundances in galaxies and therefore the conditions for planet and life formation across cosmic time. There is also a direct connection between supernova explosions and the formation of the very stars that produce them. The shockwave from a supernova, expanding outward into the surrounding interstellar medium, can compress nearby clouds of gas and dust to the point where they begin to collapse under their own gravity and form new stars. This process, supernova-triggered star formation, is thought to be one of the mechanisms by which star formation propagates through a galaxy, with each generation of massive stars triggering the formation of the next through the shockwaves of their deaths. There is evidence that the formation of our own solar system may have been triggered, or at least influenced, by a nearby supernova explosion roughly 4.5 billion years ago. The abundance of certain short-lived radioactive isotopes in meteorites, including aluminum-26 and iron-60, is difficult to explain without invoking the injection of freshly synthesized nucleosynthesis, products from a nearby stellar explosion shortly before or during the collapse of the solar nebula. The shockwave from that explosion may have compressed the gas cloud that eventually became our sun and planets. In a very real sense, the solar system may owe its existence to the death of a massive star. This connection between stellar death and new beginnings is one of the most profound themes in modern astrophysics. The cycle works as follows. Large molecular clouds, composed primarily of hydrogen and helium left over from the Big Bang, collapse under gravity and form stars. The most massive of these stars burn through their nuclear fuel in millions of years, fusing the primordial hydrogen and helium into heavier elements: carbon, oxygen, silicon, iron, and beyond. When these stars explode, they scatter these newly forged elements across the galaxy. The next generation of stars forms from clouds that include these heavier elements, and the planets that form around them are enriched with the materials needed for chemistry, geology, and biology. We are made of atoms that were created inside stars that died billions of years before our sun was born. The explosion that Atlas detected on April 11th, 2024 was one link in this chain, a star in a galaxy 24 million light-years away, completing its role as a nuclear furnace and scattering its processed material across space. The light from that explosion had been traveling through space for 24 million years by the time it reached Atlas's detectors. The event itself occurred long before the first hominids walked on Earth. Yet, the science it has enabled is happening right now, in laboratories and observatories and computer clusters around the world, as researchers analyze the polarimetric data, refine their theoretical models, and prepare the proposals that will guide the next generation of observations. The chain from a dying star to a scientific insight spans 24 million years and involves technology that could not have existed even 20 years ago. This is what makes the detection of SN 2024 GGI not just a scientific event, but a historical one. The question of what makes stars explode is not a narrow technical puzzle. It is one of the fundamental questions about the physical processes that shaped the universe we live in. The answer, still incomplete, still being actively debated, is written in the geometry of a shockwave, in the polarization of light, in the asymmetric distribution of chemical elements in an expanding cloud of gas. Reading that answer requires the right instruments, the right algorithms, and the right people willing to stay up all night when the universe gives them a chance. The researchers who caught SN 2024 GGI in its first hours understood all of this. They knew that the window would close in hours. They knew that the data would be unlike anything collected before. And they acted. The next opportunity might come tomorrow. It might come in 5 years. It will almost certainly come before this decade is out. When it does, the observatories will be watching, the software will be running, and somewhere, in Beijing or Cambridge or Santiago or Tucson, a team of astronomers will be woken up by an alert and will begin making plans to stay up through the night to catch a star dying in real time. That is the state of supernova science today, poised, prepared, and waiting. Every explosion is a new experiment. Every early detection is a new piece of evidence. And the full picture of how stars end, how the cores of the universe's heaviest elements are forged and scattered across space, is slowly, carefully, painstakingly coming into focus. To appreciate the full significance of what spectropolarimetry can reveal about supernova explosions, it is worth dwelling on the technique itself and why it provides such a uniquely powerful window into physics that is otherwise completely inaccessible. When a supernova explodes, the explosion happens deep inside a star. The core collapse, the shockwave formation, the revival mechanism, all of this occurs in a region that is physically tiny compared to the star as a whole, and that is surrounded by layers of stellar material billions of kilometers thick. No signal other than neutrinos and gravitational waves can escape directly from the collapsing core in the first fraction of a second after the explosion begins. Even light cannot travel outward through the dense stellar envelope fast enough to carry direct information about what is happening in the core. By the time light from the explosion reaches an outside observer, it has passed through the entire mass of the star's envelope, interacted with millions of kilometers of gas and plasma, been scattered and reprocessed countless times. The light we observe from a supernova at the moment of shock breakout, the instant when the explosion's shockwave first reaches the surface of the star, carries information about the outer layers of the star, not about the deep interior where the explosion was triggered. But here is the key insight. The outer layers carry the imprint of the explosion's geometry. If the explosion was symmetric and organized along a single axis, the shockwave pushed the outer layers outward faster along that axis than perpendicular to it. The star's surface did not expand as a perfect sphere. It expanded as an elongated shape, matching the geometry of the underlying explosion. The polarization of the light emitted at shock breakout reflects the shape of the emitting surface. Measure the polarization, and you have measured the shape. The specific instrument used by Yang's team, the FORS 2 spectrograph on the Very Large Telescope, is capable of measuring the degree of linear polarization to within a fraction of a percent. This is critical because the polarization signal from a supernova is intrinsically small. Even a highly elongated explosion produces a polarization signal of only a percent or two. Measuring it accurately requires long exposure times, large collecting areas, and careful calibration to subtract instrumental artifacts from the true astrophysical signal. The Very Large Telescope, operated by the European Southern Observatory at Paranal in northern Chile, is actually a set of 4 individual telescopes, each with a mirror 8.2 meters in diameter. They can be used individually or combined into a single effective aperture. It sits at an altitude of 2,635 meters on Cerro Paranal, in one of the driest and clearest regions of the southern hemisphere sky. On a typical night, the atmospheric turbulence above Paranal, which blurs and distorts starlight, is low enough that the telescopes can achieve an angular resolution approaching the theoretical diffraction limit of the optics. FORS 2, the focal reducer and low dispersion spectrograph, is mounted at one of the Cassegrain foci of one of the 4 main telescopes. It is a versatile instrument capable of imaging, multi-object spectroscopy, and polarimetry across a wavelength range from roughly 330 nanometers in the ultraviolet to roughly 1100 nanometers in the near-infrared. Its polarimetric mode uses a half-wave retarder plate and a Wollaston prism to split incoming light into 2 orthogonally polarized beams, which are recorded simultaneously on the detector. By rotating the retarder plate through a series of angles and measuring the ratio of intensities in the 2 beams at each rotation, the instrument can measure the full Stokes parameters describing the polarization state of the light. The Stokes parameter formalism is the standard mathematical description of polarization in classical optics. The 4 Stokes parameters, conventionally labeled I, Q, U, and V, describe respectively the total intensity, the degree of linear polarization along one axis, the degree of linear polarization along a perpendicular axis, and the degree of circular polarization. For most astrophysical sources, including supernovae, the circular polarization parameter V is negligible, and the interesting information is contained in Q and U. From these 2 parameters, the total degree of linear polarization and the position angle of the polarization vector can be calculated. What Yang's team found for SN 2024 GGI was a clearly non-zero linear polarization at the time of shock breakout with a well-defined position angle. This is the observational signature of a non-spherical explosion. The polarization was strongest at early times and decreased as the supernova expanded, consistent with the picture that the initial geometry was well-defined and organized, but became more complex as the ejector expanded and mixed. The position angle of the polarization, the direction on the sky in which the electric field of the light oscillates preferentially, can be related to the orientation of the explosion's symmetry axis on the plane of the sky. However, spectropolarimetry cannot directly tell you the inclination of the explosion axis with respect to your line of sight. An explosion whose symmetry axis points directly at the observer would appear spherical even if it were highly elongated, because the elongation would be along the line of sight rather than across the plane of the sky. The measured polarization is sensitive only to the projection of the asymmetry onto the plane of the sky. This is a fundamental geometric limitation of the technique, but it can be partially addressed by modeling the explosion geometry and fitting the observed polarization as a function of wavelength and time. The spectral dependence of the polarization is particularly informative. Different elements in the expanding supernova ejector absorb light at different wavelengths, creating absorption features in the spectrum. If the geometry of the explosion is not uniform, if different chemical species are distributed differently across the explosion, then the polarization will vary across these absorption features. A sudden change in polarization at the wavelength of a spectral absorption feature indicates that the element responsible for that feature has a different spatial distribution than the overall photosphere. In SN 2024 GGI, the early spectropolarimetric data showed a relatively featureless continuum polarization consistent with an oblate or prolate photosphere geometry rather than the complex, feature-by-feature polarization variations that would be expected if different chemical species were distributed in highly irregular clumps. This relative simplicity in the early data is consistent with an organized, axially symmetric explosion rather than the chaotic, multidirectional asymmetry expected from pure neutrino-driven convection. However, it is worth emphasizing that spectropolarimetry of SN 2024 GGI captured only the outermost layers of the explosion at shock breakout, the hydrogen-rich outer envelope of the progenitor star. The deeper layers, where the actual explosion mechanism operated, are hidden beneath these outer layers. As the supernova expands and the photosphere recedes deeper into the ejector over days and weeks, later spectropolarimetric observations can probe increasingly deeper layers of the explosion. This time evolution of the polarimetric signal provides additional constraints on the three-dimensional geometry of the explosion at different depths. Follow-up observations of SN 2024 GGI over the weeks and months after shock breakout will continue to reveal information about the geometry of successively deeper layers, including the layers where the nuclear burning products nickel-56, titanium-44, and other radioactive species are distributed. If the explosion was driven by a magnetorotational mechanism, these products should also show organized axial symmetry in their distribution. If there was a component of neutrino-driven convection operating simultaneously, the distribution of these products might show more complex, multidirectional structures superimposed on the dominant axial symmetry. This is precisely the kind of multi-epoch observational campaign that Yang and his colleagues are pursuing. The initial shock breakout measurement was just the first data point in what will eventually be a detailed, time-resolved picture of the explosion's three-dimensional structure, from the outer hydrogen envelope down to the innermost layers where the neutron star was born. The broader theoretical landscape in which this work sits involves some of the most computationally intensive simulations in modern science. Three-dimensional magneto-hydrodynamic simulations of core collapse supernovae require tracking the behavior of gas, plasma, magnetic fields, radiation, and neutrinos simultaneously across a computational domain spanning the entire collapse and explosion, with spatial resolution fine enough to capture the relevant physics on scales of meters to kilometers, while modeling a star with a radius of millions of kilometers. The range of relevant length scales spans roughly 9 orders of magnitude, from the quantum effects governing neutrino interactions at the femtometer scale to the macroscopic dynamics of the star's envelope at the megameter scale. No existing supercomputer can resolve all of these scales simultaneously in a single simulation. Compromise is essential. Simulations must choose which physical processes to treat in full detail and which to approximate. Neutrino transport the propagation of neutrinos through the dense, partially opaque material surrounding the neutron star is particularly difficult to simulate accurately in 3 dimensions, because it requires solving a 6-dimensional kinetic equation for the neutrino distribution function at every point in space and time. Most current simulations use simplified approximations to the full neutrino transport problem, which may introduce errors in the calculated neutrino heating rates that affect the predicted explosion properties. The most sophisticated 3-dimensional simulations currently in use run on machines with hundreds of thousands of processor cores, consuming millions of core hours of computation for a single simulated event covering the first, second, or 2 after core bounce. These simulations are run at national supercomputing facilities in the United States, Europe, and Japan, and they are constantly being refined as new physical prescriptions are developed and as hardware improvements allow larger and more detailed calculations. One of the central challenges in these simulations is that small differences in the initial conditions or the treatment of specific physical processes can lead to very different outcomes. The line between a successful explosion and a failed supernova, between a star that blows up and one that quietly collapses into a black hole, is sometimes uncomfortably thin in the simulations. Small changes in the neutrino luminosity, the initial rotation rate of the core, or the magnetic field geometry can tip the balance from explosion to implosion. This sensitivity to initial conditions reflects a genuine physical reality. The supernova explosion mechanism operates close to a critical threshold. The energy available from the revival mechanism, whether neutrino heating, jet energy, or jittering-jet energy deposition, must exceed a certain minimum to overcome the ram pressure of the infalling stellar material and launch a successful explosion. Near this threshold, the outcome is inherently sensitive to the details of the physics. This sensitivity is one reason why observations like those of SN 2024 GGI are so valuable. They do not just test the qualitative predictions of the model's symmetric versus 2024 GGI, asymmetric explosions, successful versus failed, but provide quantitative constraints on the polarization degree, the position angle, and the time evolution of the signal that can be directly compared against model predictions. A model that gets the geometry qualitatively right but predicts the wrong degree of polarization is still incomplete. Future observations will also benefit from advances in the theoretical treatment of supernova progenitors, the state of the star in the hours, days, and years immediately before the core collapse. It has become increasingly clear over the past decade that massive stars undergo significant structural changes shortly before they explode, and these pre-explosion changes affect the character of the explosion and the signals it produces. Red supergiants, the most common type of massive star progenitor for Type II supernovae, have been observed to show dramatic increases in optical brightness in the years and months before some confirmed supernovae. SN 2023 IXF, a Type II supernova that occurred in the Pinwheel galaxy Messier 101 in May 2023, was preceded by photometric variability in the progenitor star detected in archival images going back years. Post-explosion analysis confirmed that the progenitor had been losing mass at an elevated rate before the explosion, creating a dense circumstellar medium that affected the evolution of the supernova's light curve and spectrum after the explosion. This kind of pre-explosion activity, sometimes called pre-supernova eruptions or stellar wind enhancement, complicates the interpretation of shock breakout signals. If the star has been shedding material for years or centuries before the explosion shockwave hits this circumstellar material very quickly after breaking out of the stellar surface. The interaction between the expanding shockwave and the circumstellar material generates additional light and modifies the polarization signal, disentangling the intrinsic geometry of the explosion from the effects of circumstellar interaction is an active area of research. For SN 2024 GGI, the shock breakout data captured by Yang's team may have been clean enough to measure the intrinsic geometry before significant circumstellar interaction had developed. But interpreting the spectropolarimetric data fully requires modeling the circumstellar environment around the progenitor and calculating how the interaction with that environment would affect the observed signal. This is yet another area where detailed three-dimensional simulations are necessary. The interplay between pre-explosion mass loss and supernova observables is also important for understanding the full range of Type II supernova subtypes. Not all Type II supernovae look the same. Some show hydrogen-rich spectra throughout their evolution. These are classified as Type IIP supernovae, where the P stands for plateau, because their light curves show a roughly constant brightness for several months before declining. Others show hydrogen features that weaken and disappear over time as the outer hydrogen envelope is stripped away. These are classified as Type IIb supernovae and are thought to arise from stars that lost most of their hydrogen envelopes before exploding. Still others show no hydrogen at all and are classified as Type Ib or IC supernovae, arising from stars that lost essentially all of their hydrogen and helium envelopes before the core collapse. The stripping of the outer stellar envelope can happen through stellar winds driven by the intense radiation pressure of very massive hot stars, or through mass transfer to a binary companion. In binary systems, and the majority of massive stars appear to be in binaries, the two stars can exchange mass as they evolve, with the more massive star expanding and transferring material to its companion. This mass transfer can remove most of the outer envelope from the star that is destined to explode, affecting both the type of supernova it produces and the character of the explosion. SN 2024 GGI was classified as a Type IIb supernova based on its spectral evolution. This classification suggests that the progenitor had lost much of its hydrogen envelope before exploding, possibly through binary mass transfer. The relatively thin hydrogen layer remaining on the progenitor at the time of explosion may explain the clean, organized shock breakout signal that Yang's team observed. A thick, puffed-up hydrogen envelope might have smeared out the initial geometric signal before it could be cleanly measured. This is an interesting implication. The very property of the progenitor that made SN 2024 GGI a Type II supernova may also have made it the ideal object for measuring the explosion geometry at shock breakout. A different progenitor with a much thicker hydrogen envelope might have produced an equally organized explosion internally, but the signal at the stellar surface might have been too degraded to measure clearly. The clean spectropolarimetric measurement that Yang obtained may be partly a selection effect, reflecting the specific type of progenitor that exploded rather than a universal property of all core collapse supernovae. This underscores the importance of building a large sample of early detections. Different progenitor types, different explosion mechanisms, different circumstellar environments, all of these will produce different observable signatures at shock breakout. Only by systematically studying a large and diverse sample of events can astronomers build a complete picture of the variety and underlying causes of core collapse supernovae. The next decade promises to be transformative for this goal, with Vera Rubin producing potentially millions of supernova detections per year, with improved spectropolarimetric follow-up capabilities at large telescopes, and with growing theoretical sophistication in three-dimensional simulations. The science of stellar death is entering a new era. The questions that have puzzled astrophysicists since the 1960s: what exactly revives the stalled shockwave? Why do some stars explode and others collapse silently? What determines whether a neutron star or a black hole is left behind? Are finally becoming addressable with observational data that matches the complexity of the theory. SN 2024 GGI will be remembered as the event that opened this new era, not because it resolved these questions, but because it demonstrated that they could be addressed observationally. The shape of an explosion, once thought to be an unrecoverable clue lost in the milliseconds after core bounce, turned out to be readable in the polarization of light measured hours later by a telescope in Chile. In the end, that is what science does. It finds new ways to extract information from signals that initially seemed too faint, too brief, or too indirect to be useful. The universe is under no obligation to make its workings legible to us. It simply does what it does, at vast distances and on timescales, both shorter than a heartbeat and longer than the age of the Earth. Our job is to build instruments sensitive enough to catch the echoes, and minds patient enough to decode them. The echo of a star's death, carried across 24 million light-years of space in the polarization of visible light, is now part of the scientific record. The decoding has begun. The full message, written in the physics of collapsing iron cores and reviving shockwaves, is still being read. The study of supernovae extends well beyond the immediate question of explosion mechanisms. These events are connected to some of the most fundamental open problems in physics, and understanding them better has implications that ripple outward into cosmology, particle physics, nuclear physics, and even the question of what forms of matter can exist under extreme conditions. Take neutron stars. These are the compact remnants left behind by core collapse supernovae when the progenitor star is not too massive to form a black hole directly. A neutron star packs roughly 1 to 2 times the mass of our Sun into a sphere only about 20 kilometers in diameter. The densities in the interior of a neutron star exceed anything achievable in any earthly laboratory by many orders of magnitude. At these densities, matter may exist in forms that have no analogue in ordinary experience. Deconfined quarks and gluons, strange quark matter, kaon condensates, or other exotic states predicted by quantum chromodynamics, the theory of the strong nuclear force, but never directly confirmed by experiment. The properties of matter at neutron star densities are encoded in what physicists call the nuclear equation of state. This is a mathematical relationship describing how the pressure of nuclear matter depends on its density and temperature. The equation of state determines crucial observable properties of neutron stars: their maximum possible mass, their radius for a given mass, their tidal deformability when 2 neutron stars inspiral toward merger, and the frequency of oscillations in neutron star material that produce gravitational wave signals. Measuring these properties observationally and comparing them against predictions from different theoretical equations of state has become one of the primary goals of modern neutron star astrophysics. Gravitational wave detections of neutron star mergers, the first of which, known as GW170817, was detected by LIGO and Virgo in August 2017, provide constraints on the tidal deformability and therefore the radius of neutron stars. X-ray observations of neutron stars in binary systems, where the neutron star accretes material from a companion and produces X-ray emission, provide constraints on the mass and radius through modeling of the X-ray spectra and timing signals. But supernovae also contribute to this investigation through a different channel. The properties of the newly formed neutron star during the first seconds after core bounce, its cooling rate, its contraction behavior, the frequency of its oscillations all depend on the nuclear equation of state. A neutron star that forms in a nearby supernova and produces a detectable gravitational wave signal during the first second after core bounce would provide the most direct possible measurement of neutron star matter properties at formation. Combining that measurement with later X-ray and gravitational wave measurements would give a complete picture of how the neutron star evolves from its birth state to its mature form. This is one of the reasons that the prospect of a nearby galactic supernova is so exciting to physicists beyond just the astrophysical community. Particle physicists are interested in the neutrino burst, which would allow measurements of neutrino properties, mass, oscillation, and interactions that are difficult to obtain from any other source. Nuclear physicists are interested in the equation of state constraints from the gravitational wave signal. Cosmologists are interested in the distance measurement that could be obtained by comparing the neutrino burst arrival time and the light arrival time. Gravitational wave physicists are interested in the oscillation modes of the nascent neutron star. A nearby supernova would be, in the most literal sense, a gift from the cosmos to every branch of fundamental physics that involves extreme density matter or relativistic quantum fields. The last time such a gift was received was 1987 A, and the science from that single event is still being mined and published nearly 4 decades later. Meanwhile, in the absence of a nearby event, the science advances through observations of more distant events and through improvements in theoretical modeling. The detection of SN 2024 GGI represents the current frontier of what is achievable with distant events, catching the shock breakout within hours, measuring the explosion geometry through spectropolarimetry, and beginning the process of comparing the result against theoretical predictions. But SN 2024 GG also exposed the limitations of current capabilities. The very fact that Yang's team had to draft an emergency proposal in the middle of the night, get emergency approval from ESO, and race against a several-hour window illustrates how precarious the observational setup still is. The infrastructure for routine early supernova follow-up does not yet exist. The process relies on human judgment, human networking, and human luck. The right people were awake, the right proposal was approved quickly, the right telescope happened to be accessible. Future facilities will change this. The network of wide-field survey telescopes will grow. Automated trigger systems that bypass human scheduling and immediately allocate follow-up time to transient detections are being developed. Robotic telescopes instruments that operate entirely under software control with no human involvement between the trigger and the observation are being deployed specifically to enable rapid response to transient events. Some of these robotic systems can begin acquiring data within tens of seconds of receiving a trigger alert. A world with multiple wide-field survey telescopes continuously scanning the sky, connected to multiple robotic spectropolarimetric follow-up systems that can respond automatically within minutes of a trigger, would routinely capture the shock breakout of supernovae in nearby galaxies. The event that Yang's team barely caught in a race against time would become routine. The database of shock breakout spectropolarimetric observations would grow from 1 to dozens, then to hundreds. That database would transform supernova science. Statistical analysis of explosion geometries across different progenitor types, galaxy environments, and explosion energies would begin to reveal patterns that single events cannot expose. Do all stripped envelope supernovae show axial symmetry? Do hydrogen-rich supernovae show more irregular geometries? Does the degree of polarization correlate with the explosion energy? Does the orientation of the explosion axis correlate with any observable property of the progenitor system, such as binary separation or orbital orientation? These are the questions that a large statistical sample can answer, and they are the questions whose answers would discriminate between theoretical models in a way that no single exceptional event, however carefully measured, can do alone. The process of science is inherently cumulative. Each observation adds a data point. Each model prediction is tested against the growing dataset and either survives or is refined. The history of supernova science over the past half-century is a story of this cumulative process. Theoretical models proposed in the 1960s, refined in the 80s with the lessons of 1987A, further developed through the 90s and 2000s as supercomputer simulations became more sophisticated and now being tested against observational data of a quality and immediacy that was unimaginable even a decade ago. SN 2024 GGI is one data point in this long accumulation. It is an exceptional data point, the first of its kind, a measurement that could not have been made before the specific combination of survey infrastructure, rapid communication, and spectropolarimetric capability that exists today. But it is still one data point, and the science needs many more. The universe is patient. It has been making supernovae for 10 billion years and will continue to do so for billions more. Every few seconds, somewhere in the observable universe, a massive star completes its life and collapses. Most of those events will never be observed. Some will be caught by the next generation of surveys. A handful, in the right galaxies at the right distances, will be caught early enough to measure what SN 2024 GGI allowed us to measure. Each of those catches is a window into physics that cannot be replicated on Earth, into conditions that last for milliseconds and involve densities and temperatures that no human technology can achieve or sustain. The universe provides these experiments for free. Our job is simply to be watching when they happen, and to have built the instruments capable of recording what we see. In April of 2024, we were watching, and what we saw changed the way we understand stellar death. The full understanding is still being built, one observation at a time, in observatories perched on mountaintops around the world, in computer clusters running simulations of collapsing iron cores, and in the minds of physicists and astronomers who have devoted careers to answering a question that humanity has been asking for as long as we have looked up at the night sky and wondered what it means when a star disappears, or suddenly blazes brighter than all its neighbors, and then slowly, over weeks and months, fades back into the dark. The question of what it means for a star to fail as a supernova deserves closer attention because it connects to one of the most fundamental unresolved issues in the field. What determines the mass of the compact object left behind after a core collapse event? The canonical picture, established decades ago, says that stars in a certain mass range leave behind neutron stars when they explode, while the most massive stars leave behind black holes. But the details of where exactly these boundaries lie, and how they depend on other properties of the progenitor, are still poorly constrained. Observations of neutron star masses through pulsar timing in binary systems and gravitational wave detections of neutron star mergers have revealed a distribution of masses extending from roughly 1.2 to at least 2 solar masses, with one remarkable neutron star measured at approximately 2.1 solar masses. The maximum mass that a neutron star can support against gravitational collapse, the Tolman-Oppenheimer-Volkoff limit, depends on the nuclear equation of state and is currently estimated to be somewhere between 2 and 3 solar masses. But between the lower boundary of neutron star masses and the upper boundary set by the Tolman-Oppenheimer-Volkoff limit, there is a region sometimes called the mass gap, where very few compact objects have been confidently identified. This apparent gap between roughly 2 and 5 solar masses was for a long time thought to represent a genuine physical gap in the mass distribution of compact objects. The argument was that core collapse events either produced relatively low-mass neutron stars or relatively high-mass black holes with few objects in between. Recent gravitational wave detections have complicated this picture. GW190814, a gravitational wave event detected in August 2019, appears to have involved a compact object with a mass between 2.5 and 2.6 solar masses right in the middle of the supposed mass gap. Whether this object was an unusually massive neutron star or an unusually light black hole is still debated. Understanding how core collapse events populate the compact object mass distribution requires understanding the explosion mechanism in detail. If the explosion is very energetic and efficient, it can successfully eject the outer layers of the star while leaving behind only a relatively low-mass neutron star. If the explosion is weaker or less efficient, more material may fall back onto the neutron star after the initial explosion, increasing its mass. In extreme cases, the fallback may be so extensive that the neutron star is pushed over its maximum mass and collapses into a black hole, producing what is sometimes called a delayed black hole formation. The geometry of the explosion, the very thing measured by Yang's team for SN 2024 GGI, is directly connected to the efficiency of energy deposition and therefore to the likelihood of fallback. An explosion that deposits energy asymmetrically, concentrating it along a particular axis, may be less efficient at ejecting the stellar envelope in other directions, leading to more extensive fallback and a higher residual compact object mass. An explosion that deposits energy more isotropically may eject more of the envelope and leave behind a lower mass neutron star. This means that the spectropolarimetric measurement of explosion geometry is not just about understanding the explosion mechanism in isolation. It is connected to the broader question of how supernovae produce the distribution of neutron star masses we observe. Building a statistical database of explosion geometries for a large sample of core collapse events would help constrain the relationship between explosion geometry, explosion efficiency, and residual compact object properties. The connection to binary stellar evolution adds another layer of complexity. Many neutron stars are found in binary systems, either as X-ray binaries accreting material from a companion star, or as double neutron star systems spiraling toward merger on timescales of billions of years. The properties of these binary systems, the orbital separation, the eccentricity, the masses of both components, are direct consequences of how the supernova explosion unfolded. In particular, the kick velocity imparted to the neutron star at birth, a sudden change in the neutron star's velocity relative to its pre-explosion position, is a direct result of the asymmetry of the explosion. If the explosion is perfectly spherically symmetric, the neutron star is born with no kick velocity, but no real explosion is perfectly symmetric. The asymmetries in the explosion, whether from neutrino-driven convection, from jets, or from the jittering-jet mechanism, impart a net momentum to the ejected material in some direction. By Newton's third law, an equal and opposite momentum is imparted to the neutron star. These natal kicks can be measured statistically from the proper motions of radio pulsars, the neutron stars, that produce regular radio pulses detectable from Earth. The observed distribution of pulsar proper motions implies that neutron stars are born with typical kick velocities of hundreds of kilometers per second, and some pulsars have measured velocities exceeding 1,000 kilometers per second. These kicks are so large that they frequently disrupt binary systems. When one star in a binary explodes as a supernova and the neutron star receives a kick, the suddenly changed mass and momentum of the system may cause the binary to become unbound. The companion star flies off at a high velocity and the neutron star is ejected as a high-velocity runaway pulsar. The kick velocity distribution is yet another observable that constrains supernova explosion models. If the explosion is driven by a mechanism that produces a specific type of asymmetry, say, a dominant dipole asymmetry along the rotation axis, as expected from a magnetorotational mechanism, the predicted kick velocity distribution has a particular shape and magnitude. If the explosion is driven by chaotic, multi-scale convection, as in the neutrino-driven model, the kick distribution looks different. Comparing theoretical predictions for kick velocities with the observed pulsar proper motion distribution provides a statistical test that complements the direct, event-by-event geometric measurements like those obtained for SNOR 2024 GGI. Taken together, all of these observational constraints, explosion geometries from spectropolarimetry, chemical element distributions in remnants, neutron star mass distributions from binary timing and gravitational wave events, pulsar kick velocity distributions from proper motion measurements, and neutrino burst properties from detectors like Super-Kamiokande form a web of interlocking evidence that any successful theory of core collapse must simultaneously explain. No single observation is decisive in isolation, but the cumulative weight of multiple independent constraints, each probing a different aspect of the explosion physics, is what ultimately drives theoretical progress. SN 2024 GGI added a critical new type of constraint to this web, a direct, real-time measurement of explosion geometry at shock breakout for a specific and well-characterized event. Future observations will add more. The web will grow tighter, the theoretical models will be more tightly constrained, and the picture of how massive stars die will become progressively more complete. This is the work of decades, carried out by generations of astronomers, theorists, and observers who will never meet each other, who will work with instruments not yet built to study events not yet observed. It is the ordinary, patient work of science, punctuated by extraordinary moments when the universe cooperates, when a star in a distant galaxy happens to explode at the right moment, when an automated telescope catches the light in time, when a team of scientists has the knowledge and the presence of mind to make the most of the opportunity. April 2024 was one of those moments. The next one is coming.